So another way we can look at our molecules to better assign chirality is using something called a Fischer projection. Fischer projections are going to avoid using wedges and dashes, and they're going to instead use something called standard orientation, or a top-down view of the tetrahedral compound. So here, if we were looking at this compound, we'd be looking at it from above downward. And it would look like this. So everything here, you notice from above, this hydrogen and this OH would actually be pointing up at you. That's why they now have wedges in this drawing. And the chain would look like it was pointing down away from you. And that's why they have the dashes here. And we can just redraw this, which is what you would see from above, as a line drawing. But remember that when you're drawing these lines, this always represents actual wedges and dashes. If you wanted to convert it back, you'd have to remember that this is what that represents. Now, when you're using a Fischer projection, the horizontal arms, again, are always pointing out to hug you. So the horizontal are going to be converted into the wedges, and the vertical bonds are pointing away, so they would be converted back into dashes. So if I wanted to redraw this, I've actually shown an example. Left a bond off my hydrogen there. So here's a Fischer projection, and this could then be converted into this molecule, again with my wedges and my dashes shown here. Now, here's where it gets a little bit tricky. If you wanted to think about this as our projection we've seen normally, where we have only one wedge and one dash showing one thing coming forward and one going back, and the other in the same plane with solid lines like this, you actually would have to think about setting one of these two groups up at an angle into the plane so that they are in this position, a 90-degree position. And here I've rotated the OH group here so that it's coming towards me. And this is thusly going away from me. If you can imagine that happening, this is the molecule you could generate. So I would implore you to try practicing going between these Fischer projections and what they look like in our normal tetrahedral projections that we've used prior. This is going to take a lot of mental rotation in your brain, but try to look at these. And in fact, you can generate this molecule in 3D online and rotate it around and see if you can look at it in a position where the OH and the H are coming towards you and the others are facing away. And also look at it in this position where you have these two that are in the same plane, and you have just an OH coming towards you and a hydrogen going away from you. Now, if you have a Fischer projection of something, to determine the R or S configuration for the stereocenter, you need to first put the Fischer projection so that the lowest priority group is vertical. So it has to be in this vertical line here, and preferably on the left. In this case, our hydrogen is our lowest group, and so this has been rotated to put the hydrogen vertically and on the left. Then, just like before, you would number your groups and draw your arrow. So this would be group 1, 2, and 3. If we draw our arrow around, you'll notice this is going clockwise. So this would be an R configuration. Okay, so let's do a test. Here are some molecules drawn in different types of ways using Fischer projection or using our standard tetrahedral projection. And we want to determine which of the following is the R version of 2-bromobutane. So looking at these, first of all, A gives you absolutely no information as to the state of this stereocenter. And so we cannot determine if it is a S or R because we don't have any information about that bromine and if it is coming towards us or away from us. And that is actually very key for this type of problem. So A in general doesn't even give you information to find out if it is R. Now for B, the first thing I want to do is point the hydrogen away from me, remember. So if I redraw this molecule with the hydrogen pointing away from me, we would actually get this where the bromine is pointing down. We have our methyl group here, and then our other group here. So this is the same molecule. I've just rotated around and the hydrogen is now pointing away from me into the page. Okay, this molecule here already kind of has the hydrogen pointing away, so it's easy to view. And this molecule in D is a Fischer projection. So we know how to deal with Fischer projections. Remember, we want the hydrogen vertically and on the left, which it already is. So this one will be easy to assign. So now let's assign our molecules and figure out which one is R and which one is S. So to assign, remember, atomic number, this carbon, the center carbon, the chiral carbon is attached to a bromine, this carbon with 3 oxygens, and this carbon with, 3 hydrogens. This has 2 hydrogens and a carbon attachment to it. So our priority would be 1, 2, 3. And in this case, this is rotating this way, which is clockwise. So this would be R. Let's check our other ones. This molecule, again, bromine is 1. This is 2. This is 3. So this is rotating counterclockwise. It is an S configuration. Now our Fischer projection, if we label this 1, 2, 3, this would also be rotating this way, which is clockwise, meaning this is also in the R configuration. So that means you should be able to take this Fischer projection and draw this compound. These are the same. This is a little bit of a trick, and actually your book had this mistake. I already noted it, that both B and D are correct. Your book actually only lists B as the correct answer, but both B and D are correct, and you can in fact take this Fischer projection and convert it into this drawing, this molecule drawing right here. So these are both the R configuration of 2-bromobutane.